The feeling of needing sleep is chemically mediated by adenosine, a purine nucleoside. Adenosine levels steadily increase in the extracellular space of the central nervous system during wakefulness, reflecting metabolic activity and energy expenditure. This molecule acts as an endogenous neuromodulator, signaling neuronal fatigue. It primarily binds to A1 and A2A receptors. Binding to the A1 receptor inhibits excitatory neurotransmitter release, slowing down neuronal activity. A2A receptor activation, particularly in the striatum, modulates dopamine signaling, contributing significantly to the sensation of sleepiness and reduced vigilance. The accumulation of adenosine creates the homeostatic sleep drive, often called sleep pressure, which must be relieved by sleep. This system ensures that energy reserves are replenished and metabolic byproducts are cleared. Caffeine, chemically known as 1,3,7-trimethylxanthine, belongs to the methylxanthine class of alkaloids. Its molecular structure features a purine ring system, which is crucial for its pharmacological activity. This structural similarity allows caffeine to mimic the endogenous ligand, adenosine. Other common methylxanthines include theophylline and theobromine, found in tea and cocoa respectively, though caffeine exhibits the highest potency for central nervous system effects. Caffeine is highly lipophilic, enabling rapid and complete absorption across the gastrointestinal tract and efficient passage through the blood-brain barrier. This high lipid solubility ensures quick access to central adenosine receptors, initiating its wake-promoting effects shortly after ingestion. Caffeine functions primarily as a non-selective competitive antagonist at all four adenosine receptor subtypes, A1, A2A, A2B, and A3. The competitive nature means caffeine binds reversibly to the same receptor sites as adenosine, but does not activate them. Instead, it physically blocks adenosine from binding, thereby preventing the inhibitory signaling cascade that leads to sleepiness. The affinity of caffeine for A1 and A2A receptors is particularly high, explaining its potent psychoactive effects. By blocking A1 receptors, caffeine disinhibits the release of excitatory neurotransmitters like glutamate and acetylcholine. Blocking A2A receptors prevents the modulation of dopamine pathways, effectively increasing dopamine signaling in areas critical for arousal and motor control, such as the basal ganglia. The antagonism of A1 receptors in the cortex and hippocampus enhances alertness, improves reaction time, and facilitates memory consolidation by increasing neuronal firing rates. Blocking A2A receptors in the striatum is key to caffeine's psychomotor stimulant properties. This blockade synergizes with dopamine, increasing locomotor activity and reducing fatigue. At typical consumption doses, the primary effects are mediated by A1 and A2A antagonism. However, at very high, toxic concentrations, caffeine can also inhibit phosphodiesterase enzymes, leading to increased intracellular cyclic adenosine monophosphate levels, and can mobilize intracellular calcium stores, contributing to severe side effects like seizures and cardiac arrhythmias. Following absorption, caffeine is distributed throughout total body water, crossing all biological membranes. Metabolism occurs predominantly in the liver via the cytochrome P450 enzyme system, specifically the isoform CYP1A2. This enzyme converts caffeine into three primary active metabolites: paraxanthine, theophylline, and theobromine. Paraxanthine is the most abundant metabolite, accounting for about 80% of the total metabolism, and is itself an effective adenosine antagonist. Genetic polymorphisms in the CYP1A2 gene significantly influence the rate of caffeine clearance, categorizing individuals as fast or slow metabolizers. Smoking induces CYP1A2 activity, accelerating clearance, while certain medications, such as oral contraceptives, inhibit it, prolonging caffeine's half-life.
The elimination half-life of caffeine in healthy adults typically ranges from 3 to 7 hours, though this is highly variable. Pregnancy, particularly in the third trimester, can extend the half-life dramatically, sometimes exceeding 15 hours, due to reduced CYP1A2 activity. Neonates and infants also exhibit significantly prolonged clearance times because their CYP1A2 system is not fully developed. The half-life determines the duration of the psychoactive effects and the timing of subsequent dosing required to maintain wakefulness. Renal excretion accounts for only a small fraction of unchanged caffeine. Most is excreted as metabolites in the urine. The variability in clearance rates dictates individual sensitivity to caffeine's effects and the potential for accumulation. Chronic high-dose caffeine consumption leads to pharmacological tolerance, requiring increased doses to achieve the initial stimulant effect. This tolerance is primarily mediated by the upregulation of adenosine receptors, particularly A1 receptors, in response to chronic antagonism. The increased number of receptors means that when caffeine is withdrawn, the now unopposed high levels of endogenous adenosine bind to a greater density of receptors, resulting in pronounced withdrawal symptoms. These symptoms typically include headaches, fatigue, reduced alertness, and mood disturbances. Caffeine dependence is classified as a substance use disorder in diagnostic manuals, characterized by continued use despite knowledge of physical or psychological problems caused by the substance. Beyond the central nervous system, caffeine exerts significant peripheral effects. It acts as a mild diuretic by increasing renal blood flow and inhibiting sodium reabsorption in the proximal tubules. Cardiovascularly, caffeine increases heart rate and contractility, mediated partly by catecholamine release and partly by direct effects on cardiac muscle. While acute consumption often causes a transient increase in blood pressure, chronic use typically leads to tolerance in this system. Caffeine also causes bronchodilation by inhibiting phosphodiesterase, a mechanism shared with theophylline, making it historically relevant in treating asthma. These peripheral actions contribute to the overall physiological profile, but are secondary to the primary central nervous system antagonism. Caffeine's efficacy as a wakefulness promoter stems directly from its structural mimicry of adenosine, enabling competitive blockade at A1 and A2A receptors. This antagonism effectively overrides the homeostatic sleep drive signaled by accumulating adenosine. The rapid absorption, efficient blood-brain barrier penetration, and subsequent hepatic metabolism into active metabolites ensure sustained pharmacological action. Understanding the interplay between adenosine receptor density, CYP1A2 genetics, and chronic exposure explains the wide spectrum of individual responses, from enhanced performance to dependence and withdrawal. The pharmacological profile confirms caffeine as a potent, centrally acting neuromodulator that temporarily shifts the balance away from sleep pressure toward arousal.